All right, welcome to week 3 for Maps, Mapping, and Geospatial Technology. Today we're going to be talking about transforming geospatial information. So there are many datums out there, as I talked about in the lecture from last week. And it's important to know which one you're using when you are taking measurements for your map. 2 sets of geospatial data about a town that you need to bring together for analysis on one map. Basic, street map with building footprints can look entirely different on using 2 different datums, as you can see in this image on screen. Each piece of data is in a different projection and coordinate system, which can result in some interesting looking overlaid images. And when you put your data together on top of a map using a different datum, things aren't going to match up. Streets and buildings will be in different places in relationship to each other, and it's just going to look weird, basically. So it's important to note when you're dealing with geospatial data that it can be constructed using a variety of different datums, coordinate systems, and projections. It's best to try and work with all geospatial data on the same basis. And if you have multiple data layers in different map projections and you try to overlay them, those pieces of data won't properly align with each other. So projections are just mathematical transformations. It is best to reproject your data before moving forward if your data sets are using a different datum than what your map is using. So a reprojection is to transform all of the data sets to conform them to a common datum, coordinate system, and projection. Reprojecting data involves translating the coordinate system, map projections, and measurements from one system to another. And many geospatial software packages give you this capability to reproject your initial data set to create a new data set with new coordinates. So reprojecting your data without knowing where your scanned image matches up with the rest of the data, you won't be able to use this image as geospatial data or reproject it to match your other data. The same concept holds true for other types of data used with geospatial technology. If all types of data automatically had the correct spatial reference when they were created, it would just make things a whole lot easier. Problems are going to arise if one or more of your pieces of data doesn't have coordinates assigned to it, or if you don't have any information about what projection or datum was used to construct it. So what happens when your measurements don't match up? It's really not that uncommon to have multiple data sources with different projections, coordinate systems, and datums that all need to be used in a project. If everything doesn't align properly, you can end up with points being plotted in the wrong locations with respect to the base map on which they're being located, or street data that doesn't line up with a satellite image of the same area. What kind of effects could this type of simple data mismatch have on real-world companies or government agencies? So if there's a fire in a building and a fire department goes based off of a data set of where fire hydrants are located, and that data is using a completely different datum or projection than the map it's on is using, they could go to a completely different location than where they actually need to be. That's just, a brief example. It can get pretty bad if it's, not using the correct datums. So what will happen if a road renovation crew is using sewer data and street data that don't align properly because they're using different datums or projections, similar to the fire hydrant one? Similarly, what effects could such misalignments have on projects such as shoreline construction, zoning maps, or species habitat mapping? Units you're measuring, such as 200 millimeters over from the left-hand corner and 40 millimeters up from the left-hand corner. Just a couple of different examples of things that could happen. So, georeferencing is the process of aligning an unreferenced data set with one that has spatial reference information. Other terms used for similar processes include image-to-map rectification, geometric transformation, and registration. Raster data is obtained from many sources such as satellite images, aerial cameras, and scanned maps. Modern satellite images and aerial cameras tend to have relatively accurate location information, but might need slight adjustments to line up with your GIS data. Scanned maps and historical data usually do not contain spatial reference information. In these cases, you will need to use accurate location data to align or georeference your raster data to a map coordinate system. Map coordinate system is defined using a map projection, a method by which the curved surface of the Earth is portrayed on a flat surface. So this is a hands-on activity for you guys to go through on your own time if you would like to. I'll go ahead and click on the link so you guys can see what it's all about. This is information about an ongoing project for the collection and preservation of historical maps. The maps on the website are part of a collection that stretches from the 17th century all the way up to the present. So clicking on one of these, you can actually see the map, and this is of Los Angeles and San Bernardino, and it is pretty cool. If you have some time, definitely go and check this out, and you can actually see how this, kind of is warped to the shape of the globe for the projection. So it's definitely pretty cool. It's worth a look if you have some time. Control points, they're locations that are accurately identified on the raster data set and in the real world coordinates. Some examples would be road intersections and building corners. When data is georeferenced, each location in that data is aligned with real-world coordinates. To get started, you're going to need a source of real-world coordinates against which to align your unreferenced data. The choice of a source to use for the matching is important because you have to be able to find the same locations on both the unreferenced image and the source. This is super important for georeferencing because the process needs to have some common locations to kind of tie the unreferenced data to the source data. In the georeferencing process, these spots are referred to as control points. So the source should be something on which you can find the same locations as the ones in your unreferenced data. That's definitely super, super important. And then, if you have like a low resolution image, a satellite image, it might not be a good match with a detailed map of like campus buildings or something like that. It might be hard to find the exact same location. These are some example images for control points. As you can see here, these stars line up with the stars on the map. So you can make sure the two different images are lining up properly. And then similar here for control points as well. So transformations, when data is transformed or rectified, it is warped to match the source. It can be rotated, skewed, or scaled. The first polynomial transformation is commonly used to georeference an image. Use the first order or affine transformation to shift, scale, and rotate a raster dataset. This generally results in straight lines on the raster dataset mapped as straight lines in the warped raster dataset. This usually leads to squares, and rectangles on the raster dataset will commonly be changed into parallelograms of arbitrary scaling and angle rotation. With a minimum of 3 control points, the mathematical equation used with a first order transformation can exactly map each raster point to the target location. Any more than 3 control points introduces errors that are distributed throughout all the control points. You should add more than 3 control points because if one control is inaccurate, it has a much greater impact on the actual transformation. Even though the mathematical transformation error may increase as you create more links, the overall accuracy of the transformation will increase. The higher transformation order, the more complex the distortion that can be corrected, but transformations higher than third order are rarely needed. Higher order transformations require more links and will resolve progressively more processing time. In general, if raster needs to be stretched, scaled, and rotated, use the first order transformation if the raster dataset must be bent or curved. Use a second or third order transformation. Root mean square error. It's an indicator of how well the now referenced data matches with the source. After unreferenced data is aligned with the source, coordinates are computed for locations in the selected control points. And if the control points are in the exact same location, both the unreferenced data and the source, the difference will be 0. The smaller the differences between the control point on the unreferenced data and the true location, the lower the root mean square error is going to be. Rubber sheeting is the process of adjusting and distorting the geographic layer so that it aligns with features in another layer. Basically, think of control points as pins and you are stretching the map. That would be what rubber sheeting is. And then last but not least, another hands-on activity. Again, if you have some time, check it out. I definitely think it is worth a look. This one, I think is going to be a little bit more in depth. So you'll need to sign into your ArcGIS Online account, and then go through and add some layers, in order to see the different projections, and such. So, if you have some time, check it out. And that is going to do it for the actual lecture. A couple of different housekeeping items, I guess, for the week. There is no assignment for this week. Well, there's no assignment that is going to be assigned based off of the week 3 lecture material. You do still have your assignment number, I think it's assignment number 4. It's either assignment number 3 or number 4, the one with the walkthrough ArcGIS Pro. That one is due, I believe, this upcoming Sunday, so a week from when I'm recording this and when this will be posted on my courses. That is due, and then it also was brought to my attention that the assignments their due dates and times were based off of Pacific time. So for me, they were due at midnight on Friday, which is actually 3 a.m. on Saturday for you guys. I wasn't aware that it goes off of my time when I make the assignment. So from now on, they will be due at 9 p.m. on Friday, which is the true midnight for you guys. I think technically it's 11:59 Friday will be the deadline. So I do think that is about to, that's going to wrap this one up. So if you have any questions or concerns, reach out to me. I will be available tomorrow, Monday the 27th, around 11 a.m. Pacific time, so 2 p.m. for you guys for any questions or office hours. So yeah, have a good week, everyone.